Okay, so what we're going over today relates to some of the stuff we talked about last week. Okay? In fact, everything we talked about in this unit is going to somehow relate back to energy transfers, climate, factors affecting climate, all of that kind of stuff. It's all going to relate back to that in some way. Okay? Today, we're going to talk about heat capacity. Okay? Now, heat capacity is physical property. So back to the chemistry unit. Okay, physical properties are things that a substance would have that are unique to it. So for example, solubility, boiling point, melting point, color, okay, all that stuff we talked about back in chemistry. Heat capacity is another physical property. We didn't talk about it back in chemistry, but it is, and it's something that is unique to each substance. Okay? Now, here's what heat capacity means. It's basically how much energy something can absorb before it changes temperature. Okay? So what we're talking about here is, okay, something's ability to absorb energy, so joules per gram degree Celsius. How many joules of energy can 1 gram of this material absorb before it changes temperature by 1 degree Celsius? Okay? Some things have a very low specific heat capacity, which means they heat up very, very quickly. Other things have a very high specific heat capacity, which means they can absorb a lot of energy and not change their temperature very much. Water is one of those materials. Water has a very high specific heat capacity. Okay? So that means it can gain or lose a great deal of energy, and its temperature won't fluctuate very much. This is why being next to an ocean is a factor affecting climate. Okay, so that's what ties back. If you have the notes package, guys, this is in it. Okay, so it ties back to factors affecting climate because being near the ocean means you're near a huge amount of water that can gain or lose large amounts of energy and not change its temperature. Okay, so that's why Vancouver, which is fairly similar in latitude to Calgary, is much more mild in terms of its climate. Okay, it doesn't get extraordinarily hot. It doesn't get extraordinarily cold. Okay, we do both here. Okay, we like to make sure everyone feels included. Okay, whereas in Vancouver, they just kind of hover around between like -5 to like 25 degrees, okay? Whereas we go quite a bit further in both directions, okay? The reason for that is when cold air moves towards Vancouver, it has to be sitting over the ocean, okay? The ocean is going to be warmer than that cold air. And so energy is going to follow the second law of thermodynamics, and it's going to travel out of the water and into the air. The air's temperature will go up because air has a much lower heat capacity. Okay? The water will lose energy, but its temperature won't change very much. Okay? For two reasons. There's a lot of it, and it has a really high heat capacity. Okay? So that's why, kind of tied back in to factors affecting climate, we go over heat capacity. It's also something you'll use almost right away in Chemistry 20 when you start doing thermal chemistry. Okay? So, that's about all you need to know about heat capacity. Okay? Low heat capacity heats up fast. Okay? High heat capacity heats up slow. All right? Now, there is a formula that goes along with this, and it's super easy. Okay? It's like going to be one of the easiest formulas you've used yet in this course. Right? So, the amount of energy something can gain or lose is affected by not only its heat capacity, but also how much of it there is. Okay? If you had 1 ice cube in your hand, okay, you could heat it up to melting pretty quickly. Put a bag of ice in your hand, and that's not going to go as well. Okay? It's still ice, still has the same heat capacity, but a bag of ice is, well, a lot more ice. Okay? Everyone follow? Okay? It's like, I can put my hands around a glass of water and warm it up. If I put my hands in the ocean, I'm not going to do much to it. Okay? Mass matters. Okay? How much of the material there is means it can gain or lose a lot of energy. Okay? As well as its heat capacity. And then, of course, how much do you want to change its temperature? Okay, all of those things can affect how much energy is going to be needed. All right, everyone with me so far? Okay, so the formula that goes with specific heat capacity goes like this. Okay, E is the energy in joules. Okay, M is the mass, and that's in grams, because we're back to chemistry. Okay, chemistry uses grams, physics uses kilograms. This is thermal chemistry. Okay, delta T, okay, is the change in temperature. Okay, so that's obviously final temperature minus initial temperature. Okay, and that would be in degrees Celsius. Okay, and then C is the specific heat capacity. Okay, and specific heat capacity is a physical property, and that sheet I gave you has a bunch of the specific heats on it. Okay, and the units for specific heat capacity are joules per gram degree Celsius. So how many joules to heat 1 gram by 1 degree Celsius? Okay, since everything in that formula is being multiplied, does that make it pretty easy to manipulate? Right? This is basically like E equals M times G times H. Whatever I want to leave by itself, I divide everything else over to the other side, and I'm done. Okay? So there's nothing really tricky here about the algebra of using this formula. Okay, questions so far on that? Okay, so the key points here for this morning. Okay, heat capacity is the reason why being near an ocean is a factor affecting climate. The water can gain and absorb lots of energy without changing temperature. Okay, second thing, specific heat capacity is a physical property. It's different for every material. Okay, so some materials heat up fast, some heat up slow. Okay, and cool off fast and cool off slow. Works in both directions. Okay, and then this formula is on your formula sheet. Okay, so you don't have to memorize it. You do need to know what each thing is, because that's obviously not on your formula sheet. Okay, and anytime you have a question, okay, you'll get the specific heat capacity, unless that's the thing they want you to calculate, then you'd be given everything else. Okay, so what we're going to do is what we usually do. We're going to walk through one example of every type of problem you could get with this formula, so that you have an example. I'm going to have you work on a few, not too many, and then we're going to move on to latent heat. Okay, the reason I say a few, not too many, is because you don't need a lot of time to practice this. This is easy. Okay, compared to what you did in physics, this is nothing. All right, anybody need that anymore? Can I scroll it up? Okay, I'm going to have you quickly copy that one down, okay, and then we'll walk through it together. So I'll give you a minute here to copy that question. All right, so how much heat or thermal energy is needed to raise the temperature? What am I looking for here? Energy, yeah, I'm looking for E. Okay, so E is the question mark, is needed to raise the temperature of 150 grams of water. They give me two things there. Mass. And they told me what material it is, so I can find out its heat capacity. Okay, for water, it's 4.2 joules per gram degree Celsius. Okay, that one's one you're going to use a lot. Okay, we use the one for water a lot. All right, and we're heating it from 5 degrees to 85 degrees. What's our temperature change? 80 degrees. Okay, so we have M, we have C, we have delta T. That means we don't have to manipulate anything here. We just have to plug our numbers in. So 150 grams times 4.2 joules per gram degree Celsius times 80 degrees, 80 degrees Celsius. Okay, so I've got grams times joules per gram degree Celsius. That means the grams and the Celsius are going to cancel, and I'll be left with joules. That's exactly what I'm looking for, so that works. Okay, sorry guys, I forgot to fire up my calculator there. What does it come up to? How much? 50,400? 50 or 15? 50. That's what I thought. Yeah, 50,400 joules. Okay, is that a lot of energy? It is, and that's not very much water. Okay, 150 grams is about a third of a cup. Okay, so, you know, a third of a cup's maybe about that big around and maybe that deep. Okay, it's not a lot of water, but that's a lot of energy. Okay, water has a very high heat. I know 4.2 doesn't seem like a big number, but when you look at the other numbers on that list, most of them are decimals. Okay, so water actually does have a very high specific heat capacity. All right, any questions on the first one? All right, so obviously that's the easiest one. Okay. Okay, write that one down. Give it a try. Okay, we're looking for the material this is made out of. So you will have to refer back to your sheet. Okay. All right, so on this one, they're asking what material this thing is made of. That means we're looking for a characteristic physical property that's unique to that material, like its specific heat capacity. It's the only thing we don't know in this question. They do say it's a 100-gram cup, so they tell us the mass. Okay, it takes 4,200 joules worth of energy. Okay, and we're raising its temperature from 12 to 62, which means the temperature change is 50 degrees Celsius. Okay, so that's the information we have. Okay, we need to find C. So we got E equals M times C times delta T. We want to leave C over here. Okay, like so, plug in our numbers. So 4,200 joules divided by 100 grams, okay, times 50 degrees Celsius. All right, that's going to leave us with joules per gram degree Celsius, which is the units we're looking for. Okay, so 4,200 okay, divided by 100 times 50. Okay, so we're looking at 0.84. Is that glass? Yeah. Okay, so if you were doing this on a test, I'd still be looking for 0.084 joules per gram degree Celsius, and then like equals glass. Okay, on the end of that. Okay, questions on that one? Okay, that's also a pretty common type where they ask you what's the material. If they ask you that, it's because you have that chart in front of you. On a test, I'm less likely to ask for that and to give you the specific heat, ask you to calculate something else, just because I don't want to put that whole list on the front of the test. It takes up too much space. Okay, so if I give you a specific heat capacity question on a test, it'll be here's the specific heat capacity and the material, find something else. Okay? All right. Give that one a try. This is about as tricky as they get because it has one extra step. So as I said, this is the trickiest one, just because there's an extra step. You got to figure out what the final temperature is at the end. So since final temperature is not part of the formula, okay, still write down what we have. We have the mass, okay, 185 grams. It's a block of iron, so C for iron is 0.23. 0.46, it's half of that. Okay, 0.460 joules per gram degree Celsius. Okay, its initial temperature is 7 degrees Celsius. I'm looking for the final temperature, okay, which means, and I also know the energy, 200 joules, which means right now, all I can find is delta T. Right? That's all that formula solves for, is change in temperature. But if I know the change and I know what it started at, I just have to add those two numbers together and I've got my final. That's the extra step, is adding the change to the initial and getting the final. Okay? So E equals m times c times delta T. Okay? We want to solve for delta T, so we'll divide both sides by m times c. So that'll be 200 joules divided by 185 times 0.46. Okay, that'll give us the change in temperature. All right, so the temperature change is 2.35 degrees Celsius. So not very much. Okay, this only warms up by 2.35 degrees Celsius. So if it starts at 7 and warms up by 2.35 degrees, then my final temperature is 9.35 degrees Celsius. It did say it was warming up, so the temperature must go up by 2.35 degrees Celsius. Okay, everybody with me there? Like I said, that's as tricky as they get. And all you had to do was that simple manipulation and then add two numbers. Okay, do I need that one anymore? Okay. Whoa, whoa, I didn't press it that many times. Okay, on that sheet that I gave you, I would like you guys to do, circle these questions. 1, 4, 6, 9, 11, 13, 16, and 20. Okay? Now, just so you know, these go kind of, there's 5 questions of each type. There's 5 that ask you to solve for one thing, then the next 5 ask you to solve for another thing. Okay, so you're doing 2 of each type. So 2 questions that solve for energy, 2 questions that solve for specific heat, 2 questions that solve for mass, 2 questions that solve for temperature. All right? So get working on those. We'll go through any that give us trouble. I don't suspect there will be many, but if there are, no problem. We go over them, okay? And then we're moving on to the next thing, okay? This is not something that we usually spend a ton of time on because it's basically just algebra. You already know how to do that. Okay. All right, so on number 11, okay, we have the energy, 60,000 joules. Okay, it's 1.4 kilograms of water. That's 1,400 grams, because there's 1,000 grams in a kilogram. And we're looking for the temperature change. How much does it increase? What's the change in temperature? Okay, so that'll be delta T will equal E divided by m times c. So 60,000, okay, divided by 1,400 times the specific heat capacity of water. That is what she's boiling. Okay, 1,400 times 4.2, and when we plug that in, we should get 10.2 degrees Celsius. Okay, you do have to bracket the bottom. Okay, if you don't bracket the bottom, you may not get the same answer. Okay, any other ones? Questions?
So you converted
The grams, the kilograms to grams. Yeah, you have to. Because this.
How come for 9 I got it right, but I didn't have to convert it into grams?
I don't know. You put in 80 and got 960,000? I don't think so. Not with 80. Oh, on number 9, sorry, from 15 to 20. 27 kilograms of air. Yeah, you still would have had to convert that to grams to get that number. 27,000 grams.
That's odd, I got the right answer. Okay.
Are you sure? You didn't just get those numbers with a different decimal point? Like, you got 134.325? Not 134,325? 0.325, 1,000 times less. So you got the right numbers, but not the right number. This is a comma. Okay? Yeah? Okay. Any other ones? Okay, then we got to move on to latent heat here. Okay, so this is the next thing. These are in your notes. Okay, but not a bad idea to write down a few things here. Now, this stuff about latent heat is the math behind how the water cycle transfers energy from one place to another. Okay, remember the other day we drew the water cycle and we said here's where the energy goes in, here's where the energy goes out, and the in and out processes were evaporation and condensation. Right, where those two, where the water vapor is, or sorry, the water is turned into water vapor, and then where the water vapor condenses back into water. Okay, so it took energy to vaporize it, energy was released when it condensed back. So we're going to be looking at what we call the heating curve of water to see where the energy is required in the water cycle to move the energy around. Okay, so here's what we need to understand about water. It has a heating curve. We say curve, it's not really a curve, okay, but we call it a heating curve that looks like this. We have to understand or know, this is expected background knowledge, that you know that ice melts at 0 and water boils at 100. This is background knowledge I expect you to have, okay? So what we're looking at here is we've got energy on the x-axis. Okay, so how much energy are we putting in? And then on the y-axis, we've got temperature, right? Now we can see that if we start here at minus 25, we would have water in its solid form, right? Water is going to be in its solid form until it gets to 0. If I start heating that ice, it doesn't melt right away. It has to heat to freezing first, or melting first, and then it will start to melt. Okay, so during this part of the graph here where it says ice, okay, I'm just going to change the color to blue here, okay, where it says ice, okay, I'm just changing the temperature of the ice. So if I knew the mass of the ice, and I knew that it was ice, which I do, okay, and I know I'm going from minus 25 to 0, would I be able to calculate how much energy that would require? Is that the same formula you've been using for the last half hour? Yeah, okay. On this graph, anywhere where the line is diagonal, it's going up, the temperature is changing. And in those sections, I can use this formula, E equals mc delta T, because I would know the mass. I know it's either ice or water or steam. Okay, so I would know C, because water's weird, by the way. Okay, we've established that already, that water's weird. Okay, water has a different heat capacity in every state. Okay, its highest heat capacity is when it's in its liquid form. Okay, so I could go E equals mc delta T and calculate how much energy is required here. Okay, I could do the same thing here when water is in its liquid form. I would be changing the temperature from 0 to 100, so I would know the temperature change. Okay, and I would know the mass of the water. Would it be the same as the mass of the ice? If I started with 1 kilogram of ice, would I have 1 kilogram of water? I sure hope so. You know, that whole law of conservation of mass thing, you know, where you can't create or destroy matter. Okay, if I start out with a kilogram of ice, it's because I have a certain number of water molecules in their solid form. When I melt it, I still have that many molecules of water. Okay, so the mass isn't going to change. It does change to water, so the C would be different. Okay, and the temperature change would be here. Right? The same would be true up here when it's in its vapor form or steam. Okay, if I continue to heat the steam, I'll change the temperature of the steam. I'll make the steam hotter. And I can use that formula there. Okay, so what I would suggest right now, guys, is you draw that picture of the water curve and put those formulas in there. Okay, anywhere where the line is going up, it's diagonal, you can use E equals mc delta T to calculate the amount of energy. now here's the thing with that graph. There are two parts of that graph where the line is not diagonal. But on both of them, energy is still clearly being put in. Okay, the graph says the energy is going up. But here, at 0 degrees Celsius, and here at 100 degrees Celsius, the temperature is not changing, but the energy is increasing. What's happening to the water at 0 and at 100? It's changing state. It's going from, at 0, solid to liquid. It's melting. Okay? And at 100, it's going from liquid to gas. Okay? Both of those steps require energy, but we don't see a change in temperature. Okay? It's strange but true. Okay? If you doubt me, get a thermometer and put it in a pot of boiling water. I guarantee you the temperature of that water will stay at close to 100 degrees Celsius until all the water is gone. Don't let it go that far. Okay? Because it'll burn all the minerals in the water onto your pants. Really hard to clean off. I speak from experience. You don't want to do that. Okay? But once water gets to boiling, liquid water can't get any hotter than 100 degrees Celsius. Okay? At least unless you put it under pressure. Okay? But under normal conditions, you just got a pot of water boiling, that water will not get hotter than 100. Okay? Everyone with me so far? But if it's on the stove and it's sitting on the element, it's still getting energy put in. Okay? And that's because it takes a huge amount of energy to change the state of water from liquid to gas. It also takes a fair amount of energy to melt it. Okay? Think about this as kind of a common life experience. I assume everyone in here has made a snowball with their bare hands at some point. Okay? Do your hands get really cold? Why? Because the snow's cold. Yeah, okay. But what does the snow do in your hands? It melts. Okay, here's what we need to know about that. That takes a lot of energy. It actually doesn't take a lot of energy to heat the snow up to its melting point. And usually if you're making good snowball snow, it's already close to 0 anyway. So it's not like you're heating up the ice very much. The ice actually isn't that cold. But once it starts to melt, it's not changing temperature, but your hands get really cold. Okay? And that's because for every gram of ice that you melt, every gram of snow you melt, requires 333 joules of heat from your hands. Okay? And it doesn't take much to melt a gram of ice. Okay? Like if your hands are wet, you've probably melted 2 or 3 grams of ice in making that snowball. Okay? Which means your hands have lost, if it was 2 grams, 666 joules of energy. If it was 3 grams, 999 joules of energy. Is that a lot? It is. That's why your hands get so cold. That's why you can't make too many snowballs with your bare hands. Okay? Your hands are going to get really, really cold. And it isn't because the snow is cold. It's because you're changing the state of the snow from solid to liquid. Okay? That is actually what takes a lot of energy. That's why we put ice in drinks. Okay? If you have a drink and the temperature of the drink is around 4 or 5 degrees Celsius is what we consider usually to be a good cold drink. Okay? If we put ice in there, the drink will stay at around 0 degrees Celsius until all the ice is melted. Okay? And then it'll start to warm up. Okay? If you put it in like a warmer drink, something that's gotten warm, you put a bunch of ice in there, okay, the drink will cool down to about 0, provided you put enough water in there, or enough ice in there, sorry. Okay? And then, once all the ice is melted, it'll start to warm up again. Okay? But if you have even a small bit of ice, okay, it's going to take energy from whatever you put it in to melt it. Okay? Everyone with me there? It's also why we put ice in a cooler. Okay? It's not because the ice is terribly cold. The ice is usually around 0 degrees Celsius. Okay? But it'll stay in there, and for every gram of it that melts, it'll absorb 333 joules of heat. Okay? Yeah. Everybody okay with that idea? Okay, so it's a fair amount of energy required at that step. The problem is, if I use E equals mc delta T on this step, it's going to tell me no energy is required because the temperature change is 0. So we need a different formula. Okay? Here's why. Anytime you change the temperature of anything, but let's just say water because that's what we're dealing with, what you're doing is increasing the kinetic thermal energy of that material. You're making the particles move faster. Okay? Temperature measures the speed at which the particles of that material are moving. That's how a thermometer works. Okay? A thermometer changes its reading based on how many times it gets hit by the particles of the material it's in. The more it gets hit, okay, the hotter it shows because the faster the particles are moving. Okay, so a thermometer only measures kinetic thermal energy. It doesn't measure potential thermal energy. We really don't have something that measures thermal potential energy because it doesn't involve a change in the speed of the particles. What's happening when something changes state and changes its potential thermal energy is the particles get further apart or closer together if it's going the other way. So when I melt ice, okay, the water molecules are kind of held in place and they can't move, okay? But as it melts, they get further apart and then they can go around each other. It's why water flows but ice doesn't. Okay? Making some sense there? Okay? When I take liquid water and I turn it into a gas, I've got the particles this far apart, and then I turn it into a gas, they get this far apart. Okay? With me there? So it takes way more energy to change the state of something, generally, than it does to change its kinetic thermal energy. All right? So we're going to look at 2 new formulas. They're super easy, and you never have to manipulate them. They're only ever used to calculate energy in a situation like this. Okay? And they are E equals m times LF. That's a little subscript f. Okay? That's for the melting and freezing f. Okay? And up here, E equals m times LV. Okay? So these 2 formulas just involve you multiplying mass, m, times another number, LF or LV. Those are just one number. Now, LF and LV are the latent heats involved in change of state from from solid to liquid. Okay, that's LF. Okay, the latent heat of fusion. Okay, and up here, this is the latent heat of vaporization, taking water from liquid to gas. Okay, those numbers are on your periodic table. Okay, on the back. Okay, so they are right here near the bottom, okay, where it says latent heats. Okay, so latent heat of vaporization, 2260 joules per gram. Latent heat of fusion, 333 joules per gram. Okay, so if you if you froze a block of ice, let's say you froze 1 cup, 250 grams of ice, okay? You throw that ice in the pan, you turn on the stove, okay? The ice is going to heat up, it's going to start to melt, okay? While that ice is there, the water surrounding it, the water that results from it melting, will never go higher than 0 until all the ice is gone, okay? Which is exactly what we see in this graph. First, I heat the ice to 0. Then the ice will melt. Once all the ice is melted, what will happen to the water? The water will get hotter. If I leave it on the stove, right, the water is just going to get hotter and hotter until the water starts to boil. Now, which part do you think will take longer? Melting the ice or boiling off all the water? Boiling off all the water. Hugely different. Okay? It only takes 333 joules of energy to melt a gram of ice. To boil off that same gram of water is going to require 2,260 joules. Okay? You remember when I was saying in the water cycle how much energy is stored in a storm cloud? Okay? Every gram of water in that storm cloud is holding 2,260 joules of latent heat. When it condenses back into a liquid, it will release that heat. Okay? It'll increase the kinetic thermal energy of that area. That means that area will get warmer. All right? Everybody follow me there? Okay? That's for 1 gram. Imagine how many grams of water are in a storm cloud. Okay? We're talking about a huge amount of energy being moved through the water cycle. Okay? With me so far? Okay, so this latent heat of vaporization is the one we're kind of most concerned with. It has the biggest effect on global energy transfers, climate, okay, all of that kind of stuff. This is also how we cool ourselves off. Okay? If we get hot, what does our body do? Okay. Why does that make us cooler? What does the sweat do? No, it actually dehydrates. You sweat, you lose the water. Okay. Will you eventually dry off, like when you're sweating? Okay, so, right. When you dry off, when the sweat evaporates, where does it get the energy to evaporate from? From your body. So for every gram of sweat that evaporates off your body gives away 2,260 joules of thermal energy. Okay? It's why if you start to sweat and then you go somewhere cold, you feel really cold. You feel like chilled right away. You're still wet. Okay? That sweat is still going to evaporate, even in a cold situation. Okay? And that can make you really cold. It's why in the wintertime, they always tell you dress in layers. Okay? That way if you start to sweat, you take off some layers, because the worst thing you can do if it's cold outside and you're working really hard and getting sweaty is to get wet. Okay? If you become wet with sweat, you could get hypothermia, because that sweat still has to evaporate. Okay? And when it evaporates, it is going to cool you off. It's going to make you colder. Okay? If you've ever gone to Stampede, they have those big like misting stations, right? And you walk through. That's just putting a little bit of water on you. That water's not overly cold, okay? But you get a little bit of moisture on your body and it evaporates. Okay? You feel cooler. Right? It's why, like, if we put on a fan and stand in front of it, do we feel cooler? Is the fan making the air cold? No. It's just increasing the rate at which your sweat evaporates. That makes you feel cooler. In the same way that walking through that misting station, okay, puts a little bit of moisture on your skin, and when it evaporates, you feel cooler. Okay, it's also why when you get out of the shower in the morning, you're like, oh, I got to dry off because I'm getting cold, okay, because you've got all this water on your skin, and for every gram of it that dries off, okay, if it just evaporates, doesn't get soaked up by your towel, it's taking 2,260 joules worth of energy away from you. Okay? That's sort of making sense? Okay. All right, so that's how sweat works. Now, does that mean that if you sweat a lot, that you cool yourself better? Okay. You only actually have to perspire a little bit to effectively cool yourself off, but everybody sweats differently. Okay? Some people, they just get like little beads and that's all that ever happens. Okay? And then other people just, they're dripping. Okay? Being a person who sweats heavily doesn't mean you cool yourself off any better than someone who just perspires. In fact, the person who perspires arguably cools themselves more efficiently because they lose less water. Okay? If you've ever seen, like, they have before and after pictures of goalies sometimes in professional hockey, they look gaunt after a game because they'll lose 10 pounds in the course of a game. Okay? They'll sweat out literally liters of water. Okay? Back during the decade of darkness, the Oilers had a goalie named Nikolai Habibulin. This guy was one of those heavy sweaters. Okay? They actually caught on the crease cam, the little camera that sits in the goal. He had drilled holes in the bottom of his skates to drain the sweat. He sweat that much. Every time there was a whistle, he'd skate to the bench and get a new catcher and a new blocker. Okay? And they would just like wring these things out and put them on the dryer behind the bench because they'd be soaked. Okay? This is why the Oilers could never win a shootout. Okay? By the time that we got to a shootout, the guy was one full body cramp, okay? Because he had lost 10 pounds in water, okay, over the course of the game. Didn't make him any cooler, he just sweated a lot. Okay? You just need the sweat to evaporate. That's how it works. Sweating more doesn't necessarily mean you're going to cool yourself better. Okay? Everybody with me there? So also how sweat works. Okay, so is this making some sense? All right, so here's how problems related to this will work. You'll be given like a mass of ice. Say you have like 500 grams of ice at minus 15 degrees Celsius. How much energy will it take to heat it to water at 50 degrees Celsius? All right, so what you would have to do then is you would have to go, all right, I'm starting here at minus 15 degrees, and I'm going to here, water at 50. Okay, how many calculations am I going to have to do to figure that out? Or how many steps are there in this process? So I throw this ice in a pan. I start adding heat to it. What's the ice going to do? Before it melts, it's got to warm up. Okay, it doesn't melt till it gets to 0. Okay, so there would be this step where I would be heating up the ice from minus 15 to 0. I could use this formula to figure out how much energy that would require, because I know it's going to change by 15 degrees from 15 to 0. I would know its mass, and I know it's ice. So I would know its specific heat capacity, because that's on my chart, 2.116 joules per gram degree Celsius. Okay, once I get the ice to 0, then it will melt. And I would have this formula. I still know the mass, and I know LF. This is LF right here. This is the latent heat of fusion. Okay, how much energy it takes to melt 1 gram. So I multiply that by the mass of the ice. And I've got how much energy would be required to melt the ice. Once all the ice is melted, if I continue to add heat, the water is going to get warmer. Yeah. Okay, and it would go from here to there. And I could use that formula to figure out how much energy was put in. Notice I never have to manipulate anything. It's just a matter of plugging in numbers. So these are actually pretty easy calculations as long as you figure out what steps you have to do. Okay? That's actually worth a mark on a question like this. Okay? If you do what I just did, and you go, okay, that's 1 step, 2 steps, 3 steps, that's worth a mark. Okay, you get a mark for going, okay, I know where I'm starting, I know where I'm finishing, and I know that that's 3 steps. Okay, and the steps are E equals MC delta T, E equals MLF, and E equals MC delta T. Okay, and then you just add the numbers together. We're going to go over a whole bunch of that tomorrow, kind of first half of class. Okay, second half of class, we're going to start talking about biomes. I will finish biomes on Wednesday. And we'll do our unit exam review, and your unit exam is Thursday. Okay, so tonight, suggestion, probably if you were having any trouble with those questions I handed out, try a few more. You have that sheet, you have all the answers on it, okay, because we're not going to get any more class time to work on those. And obviously that formula is part of these, so being able to use it is pretty important. Okay? All right, for your final exam, okay, remember that is June 23rd in the gym at 9 a.m. Okay, the doors to the gym will open at 8:45. Be here before then. Okay, what do you need to bring to the test? Calculator, pencils, eraser. Pencils, plural, bring more than one. Even if they're the mechanical variety, you should have more than one. Okay. In terms of your calculator, make sure it is either fully charged or has fresh batteries in it. Okay? Because I'm going to clear your calculator before the final exam. I'll walk around and clear everybody's calculator. If low battery comes up when I try to clear it, your calculator goes in my pocket. I go and clear all the other calculators. Then I walk, because I'm old, I can't run anymore, to the office, and I get a fresh set of batteries. I put them in your calculator. I clear your calculator. I take the fresh batteries out, I put your crappy batteries back in, and I bring back your calculator. That means you're probably without it for a good 10 minutes. That would stress me the heck out. Okay, if I was without my calculator for a while on a final exam. So, put fresh batteries in your calculator or charge it fully before the final. Yes? Okay, that is all you should bring. Don't bring your periodic table, you're getting a fresh one. Okay, don't bring your phone. If you're caught with a phone in the final exam writing area, you get a big fat goose egg on your final. No questions asked. Okay, so find a place to put your phone. You will not have access to your locker during final exams in June. Okay, so you will need to find somewhere else safe to put your phone, okay, during that time. Okay. If you want, you can obviously bring something to eat and something to drink. Not a bad idea. Bring something exam appropriate. Okay, a granola bar, a banana, okay, and a bottle of water. Don't bring a 4-course meal to the exam. I only say that because someone did. Okay, they brought a cooked chicken, potato wedges, a salad, and a dessert, okay, to an exam. I don't know when they intended to eat it. It was only a 2-hour exam, but the whole gym smelled like cooked chicken, which was distracting to some people, so don't do that, okay? You're not gonna be there forever, so a bottle of water and a banana or granola bar is a good idea. Don't bring an orange or a grapefruit. Your hands will get sticky when you peel it, okay? So bring something smart for an exam. A 500-gram bag of Doritos is not smart, okay? Your neighbors will probably kill you during the exam for all the crinkling and crunching that will go on. So a granola bar or banana is kind of ideal, okay? So pencils, calculator, okay, and snack or drink. That's it. That's all you should bring with you. Don't bring anything else. Okay, that is all that you will need. Okay, now remember, plan for the rest of the week. Okay, tomorrow latent heat, start biomes. Okay, Wednesday finish biomes, do unit exam review, and Thursday write the unit exam. Friday, we'll go over the unit exam and start final exam review, and Monday will be all final exam review. Come with questions for Monday, June 16th. Okay, because if I'm up here and I'm just trying to say, hey, here's some things that you should maybe look at, that's not going to be nearly as useful to you as if you come in and go, hey, Coder, can we do some mole equation questions? Or hey, Coder, can we, go over the parts of the cell again? If you come in with something specific, that's better for you. Don't make me guess what you need. All right? Okay, we'll see you tomorrow.